So we're going to go through some bonding, and we're going to do through a couple of exceptions just so we feel comfortable doing those. So we can start off. So what you want to do for all of these is you want to grab a periodic table. I have mine in front of me, so that you can look at the number of valence electrons for each of the atoms. So we can do, let's do BeH2. We'll do some of the exceptions. We'll do BH3. Um, we'll do NH3, and we'll do H2O. We'll just do these. So what we're going to do, we're going to start off just by doing the dot structure, and then we'll have more formalized rules for how to deal with molecules and Lewis structures that are a little bit more complicated. But we'll start here. So boron, beryllium in this case, has 2 valence electrons. It has 4 electrons total, 2 core electrons in the 1s. We have 2 in the 2s. And so I'm going to put these 2 electrons here and here. And we have 2 hydrogens that have 1 electron each. And so we can put the beryllium. And what I'm going to do to kind of, let's see, we'll make the hydrogen have blue electrons. So the hydrogen is going to come in on this side, and beryllium will have its electrons. And so that's BH2. We could also see this as BH2, where there are no lone pairs on, this is Be. Beryllium. There is no lone pairs on the beryllium, so this is one of the exceptions to the octet rule. Boron is the next one, so this is going to be boron with 3 electrons. And we're going to have 3 hydrogens coming in. Again, we'll do the blue electrons for the hydrogen, and then we can bond those together to get the 3 electrons from the boron, 3 hydrogen electrons from the hydrogen, and we can put the hydrogens in, or we can do this as BH3. Now you'll notice that I'm not really caring about the bond angles right now. Once we learn about valence shell electron pair repulsion, that'll be a bigger deal. At this point, I'm just drawing it. We're gonna keep layering on rules to make our structures more and more accurate or resemble the structures that will match up with the physical properties that we observe in nature. NH3, we're going to start getting into molecules that are going to have lone pairs. So we have 1, 2, 3, and then 5 total. Nitrogen has 5 valence electrons. Hydrogen has 3. Get those 3 hydrogens. And so we can see that we have nitrogen, 2 lone pairs, its 3 electrons. Hydrogen will come in with its 3 hydrogens, 3 electrons each. And we can either write that in this way, or more often, we see NH3 written like this. And then for 2 lone pairs, oxygen has 6 electrons. So we have 1, 2, 3, 4, 5, 6. And then 2 hydrogens, each having 1 electron, and those will go to form oxygen. Put those there, and then the hydrogen. But more often, we will see this as 2 lone pairs, and then the line for the covalent bonds. Okay. So multiple bonds we can also write out. So if we have like O2, that's going to be oxygen plus an oxygen. And those will form a double bond. Which we often just show as 2 lines showing the lone pairs. Okay. But this is to point out again that we have this oxygen's got an octet 2, 4, 6, 8, and this oxygen also has an octet when we're counting those 4 electrons being shared in the double bond. Okay, so those are the basics, just kind of continuing on with Lewis structures. And so we have, what I want to do now is I just want to go over a more formalized way to draw Lewis structures. Now, there are many ways to do this. My way is not the only way. I will never ask you to, show your work on how you form a Lewis structure. And honestly, the steps that I will show you, you can consolidate and not write every step out in the way that we'll learn it initially. My point for you is to give you a very systematic way to assign electrons and to create a structure in a way that will systematically lead you to the correct structure every time. If you take a shortcut or you don't do some things, you'll often put a double bond where you can't, or you'll end up with more electrons than you should. And to avoid that, if you follow these steps, you'll never get in that situation. So the most important thing is that you have a Lewis structure that is correct, and you can create Lewis structures using a process correct every time, especially for molecules you've never drawn before. If you already have that method, then use it. Don't feel like you need to use mine. But this way works pretty well. So these are steps for drawing Lewis structures. Okay, so we got step 1. And so we're going to let's do for this, let's do water, because why not? So we'll do water as our beginning molecule. It's pretty simple. So number 1 is to determine the total number of electrons. This is really important because we need to know how many electrons are going to be represented in our structure, and our structure must maintain those number of electrons. So I like to make a little table, and this might seem overkill, but it is pretty helpful for some different problems. The main thing is you want to figure out the total electrons, and you're going to do that by saying how many valence electrons does the hydrogen have? It has 1. And then how many hydrogens do you have? Well, you have 2. So and actually, I'm gonna for this one, I'm just gonna write out. I want to read that back. We'll say 1 electron times 2 hydrogens equals 2 electrons. And for oxygen, you have 6 valence electrons times 1 is equal to 6 electrons. So your total number of electrons is going to be 8 electrons. This is how many electrons need to be in your structure. Okay. Now, the first thing is to determine is the number of electrons. The second is to determine the central atom. And so a way to do that is to make a little column here. Now, this column tends to confuse some students, and so I still think it's valuable. And I'm going to call this as bonds needed. Now, this is simply looking at the molecule and saying which is the least electronegative, which needs to make the most bonds. And what I mean by needed is if you look here, oxygen follows the octet rule. This oxygen has 6 electrons. It needs 2 more electrons to get 8. And so oxygen would need 2 more electrons, because for every bond oxygen makes, it gets 1 electron. If it makes 2 bonds, it gets 2 electrons. Okay. Hydrogen has 1 electron. It needs 2 to get its duet, so it needs 1. So you can look and say, okay, well, how many bonds does each of the atoms in my molecule need? And that will represent the number of electrons it needs to get its full valence shell. For oxygen, that's going to be 8. For hydrogen, that's going to be 2. So I can see oxygen is going to be in the center. Now, for water, it's actually a little simpler than that, because hydrogen can only make 1 bond. You'll never see hydrogen making 2 bonds. And so because of that, we will never have this problem. And so oxygen will be the center. So we're going to say the oxygen is the central atom. So the second step, we'll get this below. Second step in this process is to determine the central atom. Which, again, is going to be the number with the atom that has the that needs the most electrons to fill their outer shell. If you have two atoms that both are going to fill the outer shell, like let's say we have like something like SO2, where both sulfur and oxygen are in the same column, they both need to make two bonds, then you're going to choose the least electronegative atom because they're more likely to share. The central atom is always sharing more of their electrons with the outer atoms, and so in this case, you would choose the least electronegative atom. So that's the second rule. We'll get to those in a sec. So determine the central atom. And now the third one is to complete. So you're just going to attach all atoms together. So you have the central atom. You're going to attach the two outer atoms. Okay. And then you're going to attach atoms to central atom. And for the molecules we're going to draw, we're going to pretty much only have one central atom for the most part, or almost in all cases. Attach atoms to the central atom, that's number one. And then we're going to complete the octet of atoms attached to the central atom by adding lone pairs. Now, this step we don't need to do because hydrogen already has 2 electrons. It's completed its duet. That's, again, all hydrogen's going to do. So we've done this step. We'll do an example where we need to actually add lone pairs. This is a really important step. So we attach. We do not add anything to oxygen, though we recognize right now it currently does not have enough electrons. Okay. So then what you're going to do, the fourth step, is you're going to match electrons in the structure, your Lewis structure, with electrons, with total electrons that you calculated. In this case, it's going to be 8 by adding electrons or adding lone pairs. Sorry, lone pair electrons. Adding lone pair electrons to central atom. So a lot of people like to combine this, kind of just do 3, 4 together. It's really important you do it stepwise or you run into issues. So if we go here, I'm going to redraw the structure. So hydrogen is good. If we look here, and I'm going to count the number of electrons, I need 8 electrons in my structure. That's what we said up here. And so I have a 2 and 4. So currently I have 4 electrons. That's not good. I need 4 more electrons. And so I'm going to get that by adding 2 sets of lone pairs. Now I have 8 electrons. That matches with what I should have. That's how many electrons came in to this structure from the hydrogen oxygens. That's what we need to match up. Okay. And so if we've done that, if we have the right number of total atoms, now you need to make sure that there's the central atom has an octet. In some cases, it will not. That you'll have the right number of atoms, but you will not have an octet. And we'll have examples of that in a sec. So the fifth is complete the octet of the central atom by, in most cases, by making multiple bonds using lone pairs from outer atoms. And again, I'll show you an example of that. Okay, so there's situations where you will have the total number of electrons. You can't add any more to your structure, but you have to give an octet to the central atom. You're going to move atoms from the outside atoms and make bonds, multiple bonds, so double bonds or triple bonds with that central atom. Okay, so we're going to go through, and I'm going to work through one more with you, and then I'm going to give you some to work on your own. So we'll take a break here, and then we'll come back, and we're going to do a bunch of structures where I'm going to guide you through one more, and then you're going to do some on your own.